Thank you for the introduction. So again, I'm not Hussein. Hussein has some conflict, so I have to replace him. And I'll talk about our joint work that involves three institutions. It's a Jet Propulsion Laboratory, it's Carnegie Mellon University, and University of Riverside. I'll talk about brilliant scattering in silicon carbide microresonators, and we'll in general discuss self-injection locking phenomena that we observed with those resonators. So it was a joint project, and the goal for the project was observation of Kerr combs in the structure, but quality factor and power of our lasers wasn't high enough to observe it, but brilliant was there. So to start, I will first go into detail on resonant optomechanics and try to explain you the difference between standard brilliant scattering and forward brilliant scattering, and just kind of just show some history of the phenomenon. And then I jump to the silicon carbide micro rings that we integrated with small laser. Actually, it's a DFB laser chip, and we're able to observe resonant forward brilliant scattering, or you may want to call it as optomechanical oscillation. It kind of works both ways. So let's start from the basics. And if we talk about brilliant scattering, usually in the medium we have optical pump light that is coherent and it propagates in the medium. And in a case when we can achieve phase matching and we have enough power, we can start generation of a photon that is shifted by optical phonon frequency and a phonon. So in a way, this is a 3-point interaction, like chi-2 nonlinearity, we wanted to say so, which is strongly non-degenerate. So again, we just have optical pump and we have sound generated in the system. With respect to the frequency of the scattering in the bulk, it is usually defined by phase matching condition. So we have to have k vectors for the scattered light and pump light to be matched with wave vector of the sound, and we need to have matching between frequencies of this harmonics, so two optical harmonics and the sound. After kind of like writing a simple relationship, we can find expression for the frequency and wave vector value of the scattering. And as you can see, with respect of the scattering, usually it happens in the backward direction, and the frequency is given by refractive index and speed of sound in the material. So here we have the speed of sound. So it is kind of like possible to look at this explanation in more, I would say, illustrative way, and kind of like to understand what we need to achieve to get good brilliant scattering. We basically wanted to have difference of k vectors to produce such k vectors that coincide with sound k vector. And what it means, let's kind of, for example, consider backward scattering. In this case, we have light propagating forward, for example, for the pump, and then we have backward reflection and kind of like a slightly smaller frequency optical wave and sound generated. So in a collinear case, in the case of two k vectors, we can find difference of those, and we can see that it is actually coincides with difference of the frequencies of these two, and divided by a group velocity of the medium in that point. So in other words, if we have this particular configuration, we have two optical beams creating wave bit node that propagates with group velocity in the material. And group velocity of the material can be very small. It's not phase velocity, so as you know, a long time ago, people achieved in an atomic medium group velocity smaller than than even walking speed of a person. So the basic idea for phase matching in that description comes to the requirement that group velocity of bit node of two optical waves, pump and scattered wave, should coincide with speed of sound. In that case, we have phase matching, and it leads to the oscillation. And we discussed it a long time ago in 2009. with respect of application in slow light atomic medium, we try to kind of say, okay, we can actually make phonon to be matched with phonon speed to be matched with speed of bit node of the optical wave, and in that case we can create very strong interacting system, and it can be used for forward brilliant scattering, and it can be used for observation of some nonlinear effects. After we published it in 2001 in PRL, we got a comment that will say, no, it cannot be, brilliant scattering always happens backward, and it is always defined by the material properties. It is not true in case of confined media, but in the case of confined light, because the confinement can alter significantly phase matching condition. After just looking at those media, we had a conversation with Professor Shelby, and he noticed that, in fact, in any kind of waveguide or fiber, it is possible to modify dispersion in such a way that we can get good phase matching achieved between optical waves and acoustic wave. And there are two possible configurations here. For example, we have electromagnetically induced transparency modified group velocity dispersion. Then we can scatter on acoustic waves that doesn't have cutoff frequency, but also if acoustic wave has a cutoff frequency, it is possible to achieve phase matching with those frequencies as well without requirement of slowness of light. So in other words, we can modify boundary conditions, and it allows us to phase match the scattering. So in that way, we can achieve forward scattering even though it is not allowed to be done in bulk. And later on, it was used in many nanophotonic systems and in general in optomechanics. So moving forward and considering optomechanical scattering, we need to consider two possibilities. Initially, with respect of optomechanics, it was assumed, for example, that if we have a broad optical resonance and if we tune our optical pump to a slope of this resonance, it is possible to make the system oscillate and make light to interact, for example, with radial mode of a cavity. Here, we just look at top of the cavity, and this radial mode might be excited. And in case we have probability of emission of red photon higher than probability of emission of a blue photon, we can have optomechanical instability and optomechanical oscillation. Just to note that in opposite configuration, if we just tune to the opposite slope of the resonant curve, we have probability of emission of blue photon higher, and in this case we get optomechanical cooling. And people work with that for a while, and it is just an interesting subject by itself. However, this is only one configuration, and this configuration mechanical frequency is much smaller than the bandwidth of the optical mode. There is another possibility, and that other possibility we can consider the case when mechanical frequency is large. And in this particular kind of like diagram, as you can see, we might require then we have two optical modes with high quality factor, and we have optical pump in one of the modes. And then if there is mechanical frequency supported by confined medium that coincide with the difference between these two modes, it is allowed to generate Stokes light, or kind of like produced by mixing up pump mode and produces mechanical mode, and it just shifts frequency down by mechanical mode frequency. So again, we might have resonant, triply resonant in this case, optomechanical interaction. So we try to do it using surface acoustic waves because those waves allow to have very high frequencies and linear dispersion, and in addition, kind of like to achieve phase matching in this configuration, we took advantage on possibility of making nearly steady patterns of modes in microcavity. So again, we have to require two conservation laws. One is for the energy of photon and phonons, and the other one is phase matching. And phase matching in this particular case is ensured by possibility of making slow-moving co-propagating optical patterns in the microcavity. So in other words, it is possible to select and excite a couple of modes in the cavity in such a way that bit node of these two modes will propagate along the rim in the cavity, or even will be completely stationary, even though kind of these modes are kind of like both light wave propagate in the same direction. It is kind of like quite unusual because again, if you have a vacuum and you have two optical modes interacting or just interfering, the interference picture would run with the speed of light. In the case of confined medium, you can make it any. It can be negative, can be positive, or even can be stationary. It was studied long ago and shows it's possible. And here, this is a microcavity that is placed in solutions that allows to visualize this interaction with spring gallery modes in the cavity. So here you basically it's photo, it's not simulation. And here is another observation by another group which kind of like has again steady patterns created in a cavity. So now we have two requirements fulfilled. We can create two optical modes separated by mechanical frequency, and we can create k vector for bit node of the two optical mode propagating with slow speed that might coincide with speed of sound. And it allowed us to realize interaction of surface acoustic wave with the cavity. And here kind of like yeah, I think on the next slide I'll show you. In addition to that one, what we observed that actually in microcavity it is possible to realize brilliant scattering, but for that we need to make special cavity in which again we have two modes that are capable of confining Stokes wave and pump waves that we can use in the cavity. So previously, I would say like 30 years ago, it was considered like nearly impossible because people were not able to engineer the size and shape of the microcavity, but it became possible lately, and it resulted in observation. In this particular case, there are two kind of pictures that shows possibility of brilliant scattering in crystalline cavity in this particular picture, and it uses one of possible modes, mechanical modes that are belonging to acoustic oscillation in the cavity. And those modes, as you can see here, in particular, I think it's calcium fluoride. Yes, calcium fluoride. It has comparably low frequency because the speed of sound in this case is for a few kilometers, approximately 5.5 kilometers per second. So it was shown it was very efficient process, and now Brillouin-based resonant lasers are used for spectroscopy. They allow to strip off a lot of noise from the pump light, and it is a very efficient system that is produced on a chip. So with respect of surface acoustic wave scattering, we were able again to select two modes. In this particular case, we use orthogonally polarized modes and separate them by mechanical frequency. It is possible to tune frequency separation between those modes, and at in point when we have coincidence of difference between optical frequencies and with mechanical frequency, we have resonant oscillation. And here is kind of like shown the spectrum of oscillation we saw here. And in this particular plot, we show dispersive curve. It's a harmonic number versus frequency that was measured in experiment, and it just confirmation that we observe scattering of light on surface acoustic waves. And it was forward scattering. In addition to it, with surface acoustic waves, we observed interesting effects that are related to creation, as we believe, pulse on the surface of the microcavity, because the mode was very narrowband, while the spectrum that we observed was really broad, much broader. Here is kind of like how mode looks like, it's red line, and this is a spectrum we observed. So apparently the spectrum wasn't generated because of generation of all these harmonics within the optical mode, but rather it was created outside of the cavity. That kind of like our hypothesis that it happens because the pulse that propagates, mechanical pulse that propagates on the surface of microcavity modulates the coupling constant between pump light and intracavity field. Now let's go to main subject of this presentation. Kind of like I hope I introduced some history of optomechanical interaction studies in microcavities. And in this particular project, we tried to observe nonlinear optical effects in silicon carbide. And the reason to do it is multifold. It's kind of like one of those is related to very high speed of sound that kind of like that material has, and because of that speed of sound, offset of Stokes frequency from the carrier should be extremely large. If we observe backward Boolean scattering, it is comparable with what people might get in diamond, and it is very convenient for filtering out that sideband. And in addition to that, silicon carbide in general is interesting material because dopants in the material might be used in magnetometry, and it has proper and very good thermal quality that improves its thermal stabilization. So there are many advantages for this particular platform. So we created this type of resonator and looked at observations, kind of like predictions of Brillouin frequencies observed previously, and decided to do it in microcavities. What is interesting is that we just looked literature, not so many studies and not so much of results were reported, but interestingly enough, if you look at thin films, people observed kind of like Stokes and both Stokes and anti-Stokes scattering, and the frequency of the scattering was significantly smaller than expected Brillouin scattering frequency in the bulk. So we decided to try it in microcavity, and our setup is shown approximately in this diagram. So what we had DFB laser that was kind of placed in TOCAN, a standard Torlabs inexpensive and noisy laser. We had very good, not thin, but thick ball lens that allowed us to couple this laser efficiently to the chip, and this chip contained a micro ring approximately with 100 GHz free spectral range. And we were able to observe backscattering from this micro ring to the laser, and this backscattering is significant when we have laser radiation hitting the mode of the cavity. The cavity quality factor was the order of 1 million, so it was low, but still resonant feedback was significant to lock the laser to the mode through self-injection locking mechanism. For those who don't know, again, if we have a laser, and if you just take another laser and shine into kind of like our laser, we can lock one laser to the other. It's kind of so-called master-slave configuration. It is known for a long time for all oscillators. In this particular case, we just shine light to a microcavity. Again, it's just microchip, and it reflects back, and it locks the laser to the microring, and it allows keeping the frequency of the laser from drifting with respect to the cavity mode. And also, for example, if laser radiation changes temperature of the microring, laser frequency follows the changed frequency of the microring. So in addition to that, we just looked at light scattered in the forward and actually backward direction. We didn't see anything in the backward direction, but we saw forward scattering in this particular configuration. So here is a picture how it was done. So this is laser, just part of the laser with the lens, and then we have this micro lens that couples light into the microcavity, and at the output of the microchip we have lensed fiber that collected light. So coupling efficiency exceeded 50% if you look from input to output, which is not bad result. We just put some light into it, but before I go and observe the spectrum, but before we discuss detail, I just wanted to say that the spectrum was tested in two groups. It was pretty clean, and what we noticed that in addition to main mode family that corresponds to so-called T00 mode, there are actually TM00 modes, and frequency splitting between these modes vary dependent on position of our pump. well, selection of the mode. So you can see that sometimes even in this plot you can see low contrast TM modes observed. So it's important to just notice it because just presence of these two modes at proper frequency allowed us to see the scattering. We were able, as I mentioned, to observe self-injection locking. This picture explains it. So we have laser which is noisy, and this laser shines in the cavity. Cavity has low Q, so kind of still some light penetrates it, and when we hit the mode, light scatters due to internal kind of inhomogeneities in the cavity, so-called relay scattering. It happens at the same frequency as the cavity mode, and it locks the laser to the resonator. If you look at so-called LI optical characteristic, or simply just observe intensity of the laser versus current, which is transferred here to the frequency units and optical power, we can see that there is certain regions that correspond like deep, that kind of so power drops because of this reflection, and in this region actually laser locks to the cavity. To observe it in experiment, we do the following. We scan laser current and send it and put output of this chip to etalon. So when we have unlocked laser, it's noisy, it goes through the etalon, it produces modulations that correspond to the cavity frequency. So it's basically etalon kind of I would say cosine type of shape. It's very noisy because laser is not very coherent. However, in the point when we lock laser to the cavity with self-injection locking and keep scanning the current, we can see that we observe only one etalon fringe, and it basically tells us that scanning of the laser by itself is reduced significantly. So in this point, we actually, the mode keeps the laser frequency in, and what happens here, we just move with respect of the mode itself. So laser frequency moves with respect of the mode, but it is kept locked. The locking gain, or basically quality of improvement of the laser noise is kind of like in linear cases 20, but if we can transfer it to power noise, it will be like this one squared, so it's approximately 400, which is not bad, but keeping in mind that laser that we used was very bad and cavity quality factor wasn't high, it is not bad result. It just shows that self-injection locking actually works pretty well in this case. So we observe different phenomena that people used to observe in microcavities. For example, depending on the direction of the scan, when we use comparably high laser power, we can see hysteretical behavior. So, kind of like if laser moves with respect, kind of in opposite direction with respect of thermal mode of the cavity mode, we observe kind of narrowing of the resonance. When we change the scanning direction, then laser hits the mode, and temperature change of the mode moves the mode in the same direction as laser frequency. So kind of like we see artificially improved, well, increased locking range in the system. When we have a lot of thermal effects, we might also observe thermal instability. People saw it many times in glossy microcavity, so nothing special in here. It just shows that we have standard behavior in the systems that correspond to self-injection locking. Now, kind of like coming to main result, as I mentioned, we just here is log scale spectrum of the modes that we selected. We notice that there is approximately 15 gigahertz away mode that belongs to TM family, and this is our main mode that we optically pumped. And when we just put enough optical power in this mode, we observed that we have spectrum, kind of instead of just one optical harmonic, we have another optical harmonic at the red side, and probably one more here. However, as you can see, the resolution of our optical spectrum analyzer wasn't good, so it is not very consistent result unless we just prove it in other way. So what we did, we just sent the light, the output of the resonator to fast photodiode and demodulated it. And when we have brilliant scattering, we produced pretty high contrast radio frequency signal that kind of proves that we have two harmonics and we have stop slide generators there. Interestingly enough, again, we don't see 45 GHz frequency as it observes in backward brilliant scattering case. We just observe narrow line in there, and just changing temperature of the resonator, we were able to move frequency splitting between T and TM modes, and in that way we were able to tune this blue line or frequency of our brilliant scattering in comparably broad range. You can see that this range almost half a gigahertz. So what does it mean? Our kind of optical cavity modes are pretty tunable, and Brillouin or mechanical frequency is tunable as well, but not so much tunable. So this picture basically shows that we have acoustic mode in here that results in Brillouin scattering having comparably broad bandwidth. It's actually a very low quality factor. The reason is why. The reason it happens is that this acoustic wave, as we expect, is not confined to the microcavity. We just have this wave escaping it. It has comparably long interaction length, so we still require phase matching conditions to be fulfilled, but it is not kind of good enough to create mechanical mode there. So from that perspective, the scattering resembles scattering in bulk. But since again we have very thin film, we calculated that due to difference between sound velocities, all sound waves that are created in the chip just go in the substrate. Still, it kind of like it operates well, and this observation is very reliable. Just kind of like what is next? And next, I just wanted to flash this kind of like optomechanical idea that in principle, using different type of configuration, we observe that while it is possible, and usually in resonances, in the structures, people observe single phonon scattering. It is possible, kind of like when we have high optomechanical nonlinearity, it's possible to assume that it is also possible to excite next level of nonlinearity and achieve two phonon optomechanics. So far, people saw some optomechanical scattering with two phonons with configurations in which light reflects from suspended mirror. But we hope that the microring and using two counter-propagating lasers will be able to see two phonon optomechanical scattering in the future. So that's it. Basically, this is a conclusion. So we just studied silicon carbide microring, demonstrated DFB semiconductor laser self-injection logging to that microring, even though quality factor was not so good of the microring, and also we observe definite forward Brillouin scattering or optomechanical oscillation in the microring. Okay, that's it. Thank you for your attention.